Thanks, Emily, for the very kind introduction, and also thanks for the invitation. Sorry I wasn't able to make it there this time to Cambridge. So I have a picture here from Colorado last summer. This is Aspen, Colorado, where we have nature. We've got, trees and a creek, a little river. We've got wildlife, some deer, and we've got some human-built infrastructure, a bridge that the wildlife are making use of, and some power lines. And we somehow have to all be able to live sustainably together. A less happy picture from the region that I was living in is this one, which is an illustration of a cascading hazard when multiple anomalous or extreme events come together, causing outsized impacts. So in Boulder County in autumn of 2021, there was anomalous drought conditions, which in that region is snow drought. So not enough snow was falling. Actually, there was no snow in fall and winter, which is very anomalous for that location, which meant that the land cover was extremely dry. Finally, a snowstorm was coming in, and it was preceded by extremely high winds. So gusts of up to 100 miles per hour were measured, and that's anomalously high wind. So coupled with the dryness, it meant that given a single ignition, there was essentially a storm of fire. It's called a wildfire, but note, we're not in a forested area. This is mostly a grass fire. And it jumped our main highway in several places, carried on burning embers, and completely leveled, burned to the ground, several just suburban communities in the greater Denver area. And I was asked once if these white things are snow. No, that's just the charred ashes of these over 1,000 homes that were destroyed. So extreme weather events can combine together and form outsized impacts. Another example of this was in California a few years before that, in which, much as you have in some UK and many continental European areas, you'll have a lot of settlement of human communities by the coastline of a body of water, and then hills and mountains right behind that. So in the hills above the Santa Barbara region, there was a wildfire, and this is following, we're in California, so years of drought, very dry vegetation. And in the burn scar, then when an intense rainfall fell, since the understory and the most of the tree structure had been burnt out, this caused a rapid landslide or debris flow. These are very scary. Picture huge boulders coming into your living room. And, unfortunately, there was a significant loss of human life in addition to the damage to communities and infrastructure. So motivated by these cascading hazards and extreme weather, and more generally by the climate change that we've been seeing and its effect on communities and ecosystems, I work on climate informatics based on the vision that machine learning can shed light on better forecasting and better confronting climate change. So that's why I was really excited to come talk to you at this summer school, since these are very much related to the goals of ICCS. Now, there's starting to be, public awareness that AI, in addition to advancing industry, can and should be used for the benefit of society, and in particular for environmental issues. The World Economic Forum put out this white paper in 2018, basically calling for AI to be harnessed for helping us to save our environment. And as Emily referred to, this climate informatics community is now having significant critical mass. I'm not going to mention all the bullets here. I started pushing this idea about 15 years ago, actually. Some of our workshops were held in Boulder, then eventually we went international. Of course, during COVID, we went online, hosted by Oxford. Sorry, I won't say that too loud. But then this year you were in Cambridge. But as you try to build an interdisciplinary community, I just wanted to share some lessons that we've found. One is that we need places to come together, and keep in mind those coffee breaks and the punting and the lunch times, because that's when the casual interaction can form, and interactions that you make with fellow students can lead to collaborations. In Boulder, this took the form of hiking or drinking beer. We also needed a place to publish. And so we started having conference proceedings. Any computer scientists in the room are happy to publish in conference proceedings. Anybody else would prefer a journal. And so Emily also mentioned that we now have a journal on the more broader area of environmental data science. Probably everything y'all are learning here, if it leads to publications, would be great to submit to the journal. The other thing that we learned was the value of hackathons. And I was very excited to see that you'll be having a hackathon at the summer school, because generally we would engage with a domain scientist or expert that had some scientific problem, and they would help us curate a data set on which to run a challenge problem. And so this not only created data sets, but it created individual teams where some people more had climate knowledge, some people more had machine learning knowledge. We had to make sure, at least one person could program. And these small teams led to writing papers together, writing grants together, and forming those collaborations. So hopefully that'll happen for you this week. And also in the meantime, go across to other parts of your campus, find people that are doing data science if you're a climate person, and vice versa. It's really those individual collaborations that push things forward. So I wanted to use this time to talk about the 3 ways that I think machine learning and AI can help in addressing climate change. The first one is specifically when used for climate science. And the second one gets back to those pictures at the very beginning. When we talk about the storms and the things that are already happening yesterday that we already needed to be better prepared for, to reduce the loss of life and infrastructure, we're often talking about climate adaptation. And then finally, machine learning can help accelerate the transition to more green and circular economies, renewable energy. And it's debatable whether this would actually mitigate climate change, but the hope is to at least steer us away from the worst possible risks and the worst possible scenarios that could be projected. So I'm sorry, there's some construction. I hope you can adjust me so that I'm being heard okay. Are there any audio issues?
No, we
I
can
just
hear you
realized
okay.
Is it okay?
Sounds good, yeah.
Okay, yeah, I'm hearing some sort of drilling, but if it becomes bad, just interrupt me and I'll dig up my headphones. So this is more of sort of a survey of these 3 directions where machine learning can help, with examples from my lab where I've done a lot of past work in ML for climate science, currently really excited on ML for adaptation and extreme weather, and also climate equity. And then I'm starting to work also in machine learning for speeding up the transition to renewable energy. And also I am at University of Colorado, but I'm also at INRIA Paris, which is the French National Lab on Computer Science, where I'm building up a team on these topics. So if you want to hop across the channel and come visit, or are looking for a job, just to let you know, these are the kind of thrusts of that team that we're building here at INRIA. The other thing is, for folks in the room that kind of stumbled into one of these summer schools or projects, but you're actually a core machine learning person, yes, you care about climate change, but you want to advance in the domain, definitely new algorithmic open problems come up. I won't linger too much on this, but I will mention that, we like working at this sweet spot that also advances and addresses new open problems in the core machine learning methodologies. So what is so unique about this domain? So as an AI person, we would call, climate science or addressing climate change as a domain, and it has particular types of data. So it has paleoclimate data, and this is really, as opposed to maybe a big data problem, it's heterogeneous, smaller data sets. Now, some of them do go very far back into time. So there are some biological proxies of temperature and atmospheric concentration, such as looking at the rate of growth of trees. And this can also be done with corals from the ocean. It can also be done with sediment cores taken under lakes, because there's living organisms or dead organisms that flourished under certain temperature and nutrient conditions. You may have heard of ice cores, vertical columns of ice extracted from glaciers, where air bubbles actually can tell us about atmospheric concentrations, and water isotopes can be used to infer temperature. So these are excellent records that go very far back into geologic time, but spatially they're sparse. They're only in a few locations and, not evenly distributed. So it's interesting if you're interested in things like sparse matrix or sparse tensor completion, and it's one of the kinds of data that we have. Currently, we are in what's called the observation era. I'm sure everybody in this room, maybe in the lab that they're working on, has some very large data set that they have access to. And in terms of observation data, we have many remote sensing products coming from many satellite missions. We have all sorts of in situ sensors and weather stations, and various other types of floats going in the ocean, balloons in the air, and then instrumentation applied to our shipping and air transit commercial products as well. So this is a lot of data, and this is mostly good from the point of view of machine learning. I would say the only kind of caveats here, right, are that when you do have data that's extremely high dimensional, then comes a task of trying to reduce dimensionality to a certain point to find the relevant information. And then also what you'll notice is we're getting better and better spatial coverage, but of course these don't go back very far in time. So not nearly as far as some of those biological proxies we had mentioned above. But then sort of the kicker, and why I think this is a really exciting field to work on, unlike pretty much any field of collaboration that other folks in machine learning work on, is that very smart people have been generating fake data, which is the output of climate model simulations. So, these physics-driven simulations are simulating the atmosphere, ocean, land, and cryosphere. I'm sure you're hearing a lot about it in your program and in your summer school. And so I'm saying it's fake data, right? Because it's the only lens we have into the distant future or the distant past. But it does encode, first principles in science, that all the physics is respected. And then there are also some caveats in that, of course, we can't simulate everything at scale, so discretizations need to be made, and et cetera. But it's very unique to have had people working on this since the late 60s to model the phenomenon that we're trying to use AI to also better understand. So it's a wonderful complement to the observation data sets that we do have. Okay. So that first axe I was talking about is how machine learning can help in climate science. And there's a lot of ways then that machine learning can directly help in climate modeling. There's other groups doing that, and I'm sure you'll hear from them during the course of the grants that you're on. I'm going to more talk about what if we just, again, treated climate models as black box predictors, like they generate forecasts or projections. And just to get a little bit more into detail in a climate model, you've got the atmosphere, ocean, land, and cryosphere. You've got energy and heat conservation laws, and then you have process models. So, partial differential equations for energy transfers, heat advection, and et cetera, where the science of those is very well understood. But what becomes hard is how you model this at a global scale. First off, some clouds made it into the picture here, but clouds will not be in the global scale models unless we get very new generation models that have smaller grid boxes. But right now, the grid boxes are too big. And what do I mean by that? Well, to really understand a cloud, you have to reason about whether water is going to condense on an aerosol particle, and that means you're at very small spatial scales. Climate models are getting finer and finer resolution, but typically think on the order of tens to hundreds of kilometer-sized grid boxes in your 3 dimensions. And so the moist processes are not going to be explicitly resolved. In terms of the temporal scale, we know that the atmosphere circulates on the order of a few weeks, yet the ocean circulates on the order of hundreds of years, and somehow these have to be coupled. So there's some very hard problems in the simulations themselves, and this explains, this is one reason why when we look at models coming out of the UK versus a couple models in France or Australia, Germany, the US has a few, the models, each of them involving laboratories of many scientists working for many years, have generally now gotten some consensus on what has been observed historically, but they start to diverge from each other when we let them project out into the future. The idea is you can start with initial conditions, then you can let these models run and measure their temperature and other variables into the future. What they're really great for is things like attribution. What if we simulate different scenarios? Can we cut emissions a certain amount? Can we do other interventions? How would that change the model simulations? So one thing we've done, and I want to make sure people are not confusing AI with deep learning. I will talk about deep learning later, but online learning, which are these very lightweight, non-deep algorithms, can be used to take climate model forecasts from all the different countries and try to adaptively combine them by also using observations. And that's been a line of work that I'll do a quick vignette on the next slide. And then, this is about climate science, this particular axis of research, but it ties to also the extreme weather that we're seeing via things like the El Nino Southern Oscillation, right? The El Nino Southern Oscillation is known to correlate with droughts in some regions and floods in other regions. And often it can be correlated with a lot of our observed weather. So understanding it and other modes of variability in our climate system is, of course, important anytime we want to do short-term predictions. But to add another complication, ENSO itself as a pattern might be changing with climate change. It's hard enough to predict now because it doesn't have a regular period. It's on average every 5 years, but it could be, take as long as 9 years to repeat. And so one way AI can help is learning new indices for ENSO and other such important oscillations that govern what kind of weather we actually observe. So historically, a certain region in the Pacific is being looked at to monitor whether we're going to be in an El Nino or La Nina season based on the heat content and how it differs from average. So we call that a sea surface temperature anomaly. But why that particular reason? Well, there are historical reasons, but it would be very interesting to do different data-driven studies. And we can do such data-driven studies. One type you might think of just as computer vision. Let's grid up the whole ocean and see which regions are more predictive of anomalies in which other regions. And then we can also use techniques from causal analysis to say, well, if this ocean region is hot, then, or is anomalously, having a high sea surface temperature, then on a 1 to 3 month time scale, where does that, temperature move to? And look for sort of information hubs or causal relations. So that's a whole interesting direction. And then I'll also mention one thing you can use models for is infer into the future a model that you might learn on historical data where you do have observations. There's this wonderfully precise satellite-based way of measuring sea surface height out of the NASA Sea Surface Topography team that now on a 30-year record shows a mean sea surface height increase of 10 centimeters. But again, the data is only 30 years long. Now it is monthly and it is at some geospatial set of orbits, the orbit creates a nice grid, but that's not a huge amount of data to be able to generalize from. So using the climate model and various large ensemble force responses, we can try to get a handle on projecting sea level trend into the future, both at global and regional scales. It's quite ambitious, but there's a few things that we can do with that so far. So just one vignette on machine learning for climate science, which is about how do you combine the prediction of an ensemble of climate models. So think, models from all the different countries that inform the IPCC. Well, from our past work on online learning, which can often be motivated, you want to have data. Okay, so standard ML in your textbook, the theory behind it is going to rely on a statistical assumption known as independently identically distributed data, which means the data comes from a probability distribution, and that probability distribution is not changing over time. Well, when you say climate change, clearly we're not in that static setting. We're not in the IID setting. Before working on climate change, though, the kinds of examples I took for this non-stationary setting were things like the stock market, right, where you can have big regime changes. So the idea is to get a probability distribution that is not static, that is updated over time. So it's dynamically shifting based on changes in your observations, and that distribution can be used to put sort of more belief and more weights on some climate models as opposed to other climate models. And then you can also assume and then exploit your assumptions of local structure. So if you have a model coming out of the UK that's very good at creating forecasts in the London area, maybe you might want to assume that it could also have pretty good forecast skill over Cambridge because they're nearby. And this is just a silly schematic of running our algorithm that's learning the non-stationarity over time, now running it in a spatially distributed way and sharing influence in the way that I mentioned. But the neighborhood structure itself could be more complicated than this, or it could be learned from data. And doing this, actually just popping out to the core ML people, if there are any in the room, this was open in machine learning. There wasn't a distributed online learning framework to analyze such algorithms. And that led to a fun problem to pitch to some theorists. But you can also consider neighborhood similarity in time. And what do I mean by that? Well, it wasn't until I worked on this application that I heard of the following framework, because I hadn't heard of it really in AI, although it turns out it was applicable to finance as well, which is that in January, I need to make a forecast for February, but also one for March, April, May, et cetera. So I'm outputting, say, 11 forecasts each month. And then, now in February, I again output forecasts for each of the next 11 months. In ML jargon, we would call this prediction these predictions at multiple lead times, we could call each of those predictions prediction tasks as a machine learning task. And then we could do multitask learning, which is we try to learn for all lead times simultaneously and share information to improve our forecasts. Just a very simple way of sharing information would be saying, for example, okay, if the UK model is good at forecasting London from January to June, we can assume it'll probably be good for May and July, because those are neighborhoods in time. And we found that actually then learning these jointly improved performance on all forecast tasks, except actually the one with the most recent data update. So if you're trying to only predict a month in advance, then you get new observations every month. It doesn't necessarily help you to look at your neighboring task, which is the 2-month task, which has slightly more stale data. Okay. The second sort of axis that I'm interested in pushing, and where we have seen that machine learning can help, is on extreme events. I'll class this under climate change adaptation. And I started with those scary slides about cascading hazards. We are not there yet. We're even still trying to talk about how to use AI to improve detection and then forecasting of individual hazards. So I thought I would do a vignette for this talk on avalanche detection. So we'll see that on the next slide. But what is this picture here? This is a storm track forecasting problem that we did, where we treated real valued fields of wind and pressure at different geopotential heights as images, meaning, then we can use convolutional neural networks from deep learning. And so we created these registered data sets where a lat-long grid box of 25 degrees by 25 degrees would be segmented around a lat-long position of a storm center, given a data set of storm tracks. So don't ask me how they get these storm center locations, but NOAA has this wonderful data set of all the way down to tropical depressions, I believe 30 years back, in all the different basins, where every 6 hours there's a measurement of a latitude and longitude point. And so you get these tracks. And so our task was to forecast either just the next location 6 hours ahead, but we also did studies on forecasting 24 hours ahead. And it was a supervised but pre-trained CNN approach that was doing data fusion, because we were using wind, pressure, and then also past a few steps of the past track data. It was competitive, measured on historical storms, with what the National Hurricane Center was using at the time. They have a meteorological model and a statistical model, and the errors were all around the same magnitude among the three methods. But just like you're seeing now with ChatGPT about hallucinations and the creativity that can come from training these data-driven AI models, sometimes the AI would actually predict that a storm would turn sooner than the other two models on a storm that actually did turn. So you certainly don't want to replace these with what is informing the human experts, but add it to their bag of tools for decision support. The other thing I'll mention, and this kind of gets back to some of the work we did on ENSO, is that certainly at the Met Office in the UK, and but also in other countries like at IMD in India, AI is starting to be incorporated, especially because some of these extreme weather events have outsized impacts on the whole GDP. The GDP of the Indian subcontinent is extremely affected by what kind of precipitation extremes in terms of dry or extremely wet events you're going to have from each summer's monsoon that affects the agriculture and infrastructure. And then the last thing I want to just highlight is this older work of ours with a different unsupervised method that highlights what can be done with unsupervised learning in this domain, which is sort of interesting. So I had a very analytical machine learning student, and I said, we're working on extremes. And she looked that up. She looked at some expert summary of extreme events from the IPCC and found a lot of different definitions, like temperature goes over some particular threshold, or precipitation is lower than some threshold for some other threshold number of days. So we kind of feel are like hard-coded, not very probabilistic, and often only depend on one or a few variables. And we were looking for a more data-driven definition or signature for different kinds of extreme events. And so using latent Dirichlet allocation, which originally came on the scene through natural language processing, a problem called topic modeling, but just generally the idea is sort of a Bayesian hierarchical style clustering. We were able to get multivariate probabilistic definitions of extreme events, and more generally, just the different climate topics that were learned from our multivariate climatological variables, based on how much observations differed from local averages. Some of the topics were just weather as usual, but a few of them corresponded to extreme, like a very type warm and drought type event and extreme wet events. And then this was very new, and there was no analog to this in the literature. So what we did was we just sort of plotted the extremes that we learned that corresponded to a hot event and see if we could recover historical droughts, and we're able to validate it that way. Okay, so at this point, I'm going to do potentially the longest vignette. Actually, there's no real vignettes after this, on avalanche detection. And this was work with Météo France. And this is an example where you have a little bit of in situ measurement and then a lot of remote sensing product. So there is synthetic aperture radar imagery that's basically observing these regions in the French Alps where there's various backscatter and reflectance coming off of your snow up there. But then there's a ground truth survey they had taken where trekkers, humans actually had to go into these dangerous couloirs or avalanche corridors and record when they had seen avalanche deposit. Was there an intermediate data product? So an AI person would probably ask for a SAR image that had been hand labeled or segmented by an expert to show where the avalanche deposits had fallen. And at the time that we started this collaboration, there was not such a product. They said, we tried to label it, but it's very hard to see with the naked eye the differences in texture of snow when an avalanche has fallen or not, just from the remote sensed SAR imagery. So we didn't have that. So what does this sort of data set and the problem of avalanche detection mean in machine learning jargon, or what are the challenges? So one challenge we might call class imbalance. So the number of image patches with known avalanche deposits in them is quite small. These are rare events. And so if we treat those as the positive examples, then we have many, many patches that don't have them. We have many more negative examples than positive examples. Now that's going to happen anytime you study extremes, because extremes are rare. So we don't have a lot in historical data. Coupled with that, though, was that we just have some fixed and limited amount of labeled data. And more generally, this framework is the framework of semi-supervised learning, where you as the learning algorithm have not gotten to choose which data points are labeled or not. And in this case, that labeled set is extremely small. So to approach the first part of the problem, class imbalance, we're probably going to be doing some sort of anomaly detection. And, recent works at the time were learning a VAE which I'll get to in a second, a kind of unsupervised method on the negative examples, on image patches without avalanche in them, with the idea being that now when I want to classify an unlabeled image, I send it through this model that was trained on negative examples. And if the model is not good at reconstructing that image, then it must be quite different from the training data, and I can classify this as an avalanche. Okay, but that only addresses that first problem about class imbalance. This is not great for my second problem, which is that I have very few labeled data. Why is that? Well, labeled data, I don't know if you can see my mouse, is used at this kind of hidden step 1.5 that would have to happen before step 2, which is that I need to extract negative image patches without avalanche. How do I do that? Well, I have to touch my gold ground truth survey that trekkers took on the ground, which I should really be locking away for later. But I actually have to touch it and use it to label image patches from SAR. So in some sense, I've basically wasted some of that data to generate negative image patches. Then the other place, 2.5, is where I would need to use labeled data, which is to tune the hyperparameter. The hyperparameter here is the threshold on the value of the threshold on which I should say that this is an avalanche, and that has to be tuned on a labeled data set. So we can't skip 2.5 because anomaly detection is part of a longer pipeline that in the end has to give a class label, avalanche or not avalanche. So we need to tune that hyperparameter. So instead, we're going to skip 1.5. And so we're going to replace step 2 with just saying train a VAE. So don't label your data first, just extract image patches from SAR, not knowing if they have avalanche or not, just unlabeled image patches, and train your VAE. Okay, so I know that there's mixed preparation, and so I thought it might be a little bit helpful to review VAE. Some of you know what it is, but just in case. So it's actually a very dumb machine once trained. It's a machine that nobody really wants. It's basically like a noisy function. It's a noisy version of the identity function, because you can give it an image and then you send it through this machine and it outputs kind of the same image, but a bit blurrier. So nobody wants this machine. But why do we do something like this? This is an example. This is like the classic example of what is very important right now in deep unsupervised learning, which is designing pretext tasks. So this task was to fit weights, train a model in a way that you're trying to pull your output close to your input. So you have some loss function like reconstruction error on your output, comparing it to the input. These are grayscale images where humans had been asked to draw digits. Okay. What is it a pretext for? Well, once all these weights are trained, if you've sent your data through a bottleneck, so a part of the architecture that is a lower dimensional layer than your input and output layer, then the hope is that this will be a compressed, or we would call a latent representation of your data, a lower dimensional representation of your data. So learning that whole machine was just a pretext for what we can find in its bottleneck and how that represents the training data it was trained on. Okay, so usually you, probably in this domain, you will usually see dense autoencoders where we go through a bottleneck, meaning force things through a layer that has lower dimension than the input. If you talk to people across campus that work on cognitive science, you know, they might talk about a wide autoencoder where you actually project to a higher dimension. And there's evidence that in some cognitive systems, cognitive creatures project observations to higher dimensions, because then they have sparser representations and they can keep different observations separate from one another. But I think in climate, we'll probably mostly go to lower dimensions. And then this encoding that we get is the latent representation. But since we've trained on many, many images, it would also be nice to have a probability distribution over latent representations. And the first version proposed in the literature doing that would start with some very standard spherical Gaussian prior, and then adjust the parameters of the Gaussian while the learning went along. So learning some informative but still Gaussian distribution over the latent space. Okay, so back to our task. The standard approach that we mentioned first would have that step 1.5 where we have to label the images. So we take our SAR images, we take our ground truth labeled data from the terrain to extract patches that don't have avalanche. And then this whole architecture has to be trained. What does that mean? This is my VAE, and I'm fitting, don't worry about the fact this is called encoder and decoder, but I'm fitting weights at different layers. And how am I doing that? I'm doing gradient descent on this reconstruction error, comparing the output to the input. Oh, and there's a regularization, making sure I don't go too far from my Gaussian prior. But so I train this in the standard VAE training. And what we were saying is our twist is, let's skip this step. So the alternative training would be that we just extract image patches and we haven't even touched our ground truth data, so we don't know if they're negative. And then still we train a VAE in the exact same way as before. Okay, so whether you do that standard technique or our technique where you only do it on the unsupervised patches, you still, as I said, are part of a larger pipeline that's trying to do anomaly detection, which means at the end, I have to output an answer, avalanche or non-avalanche, on a new unlabeled image. And this is sort of the supervised part, the classifier functionality to classify avalanche or no avalanche. And that means that I need some labeled training data. So here now I do look at my survey to get patches that do have an avalanche and patches that don't have an avalanche. I don't do any further training. The VAE was trained in the previous step, but I do tweak this threshold, this hyperparameter in green, until I get as low of an error rate as possible, meaning most of these guys I do label +1, and most of these guys I do label as 0, no avalanche. Okay, by doing a search in the space of this threshold. That would be done for both of the methods, because that's tuning the hyperparameters. And then in both cases, the full pipeline would be used as follows. An unknown image comes in. I feed it through the trained autoencoder. Then I compute the comparison between the input and the output. That's my reconstruction error. And I compare it to the threshold, and that gives me a label. The threshold had already been tuned using the labeled validation set. Okay. So this is a hard problem. You're not going to see very strong accuracies for any method. And the baseline method does not harm any machine learning at all. It's just some sort of thresholding on the different channels that you get out of a SAR image. And in our first attempt, where we use supervised learning, CNN learning, we couldn't even beat that non-AI baseline threshold. Well, that's because of the class imbalance. So we had to use an artificially balanced data set, which was a lot smaller. And so the methods using this pipeline performed better, but the biggest lift was when we used our version of the pipeline where we trained the VAE in an unsupervised way. We didn't first filter out and train only negative examples. This is going to be counterintuitive at first. You might be bothered by the fact that, hey, this bottom row was trained with image patches that may or may not have had avalanche in them. True. First off, avalanches are rare, so there's very few such patches. But secondly, by including them, we're kind of having more noise in our training, or to put it another way, we're seeing more of the parameter space, or the feature space. And generally, we know that training on noisier input is one way to battle against overfitting and helping us to generalize. And then to sort of cement that intuition of how that works, just keep in mind that there's this two-stage, every method that's trained gets trained on the training data, but then separately, its hyperparameter, so its classification threshold, gets tuned on that labeled data set to have the best performance possible for that model at that wrapper anomaly detection or classification task. So these two methods are going to have quite different values of their threshold because the resulting VAE is different. But that threshold gets optimized after to have as good performance as possible. And these sorts of results hold up when you look at ROC curves, etc. So that was the vignette. And before getting to that last direction where I think machine learning can help, let's look at the outlook here. So it was an avalanche detection problem, but more generally, this relates to detecting rare events. And when you want to study rare events and you have very limited labeled data, what we advocate for is lean 100% or as much as you can on unsupervised learning and use that very gold precious labeled data only for what has to be done for supervised learning, in particular, tuning your hyperparameters on a labeled validation set. And then in terms of the implications of this, what we've got then is a virtual sensor, right? So hopefully, we can not force people to walk into dangerous avalanche corridors because they did so, and we've learned from their data a mapping from the remote sensed data to an avalanche detector that doesn't require the human to go in as a sensor. But more generally, when might this be helpful? So first off, anytime we don't have future observations, but maybe we have climate model simulations, then we can learn from climate model simulations to historical observations, and then have an AI way to generate, fake future observations. So that's one example of how that can help, because we don't have observations in the future. But this also drives at the heart of addressing inequity, in that this will help us address the fact that some regions are more data rich and other regions are more data poor. Whether domestically, like in the US, it has come to light that there are regions of the US that do not have good radar coverage, and it's related to decades of climate injustice, and that needs to be fixed. But AI can help learning from ubiquitous remote sense products to kind of get a virtual radar measurement for regions that are not actually instrumented. Or if we think about, the global north that's highly industrial and the global south that for the most part has been bearing the brunt of global warming, that also aligns with regions that are more sort of data rich and highly measured, and regions where we have more sparse and patchy data. And I'll quickly mention, and this is in light of the final axis, that we are wrapping up a project where we're using machine learning to help downscale climate model projections of solar irradiance to the local scales that are needed to do renewable energy planning. And in the US, we had enough data that we could use both supervised methods for downscaling and then also compare them to our unsupervised learning methods for downscaling. And then we could port those to data poorer regions, such as in India, where we have to either use an unsupervised model or just fine-tune a little bit a model that was largely trained in a data-rich region. So yeah, the final axis, and this is the newest for us, we've just been working the last few years, is on helping with the green transition. And so far that has meant renewable energy. So in the US, we were working with the National Renewable Energy Lab. And if you have a market where capitalism, or basically the bottom line, determines the energy choices that grid operators are making, then you want to make it cost effective for them to incorporate renewable energy sources. But renewable energy sources have some uncertainty associated with them. When is it going to be sunny enough? When is it going to be windy enough? And that uncertainty pretty much translates directly to cost, because you have to balance the load and you have to be ready, perhaps with a quick to warm up, but not very carbon neutral energy source, because of that uncertainty. So this is actually a really neat place for AI that focuses on forecasting algorithms to come in, because just even a small lift improving your forecasting of, say, that solar irradiance can cause a price decrease to help incentivize grid operators to turn to renewables. So maybe I'll just briefly say, and I don't want to linger on this because it's more of a machine learning item, but we had that tutorial on variational autoencoders, and from a methods perspective, you might have been frustrated that you were just learning a Gaussian over your latent representation. The development that came later was normalizing flows, where you can take something simple like a Gaussian, but then you can map it and complicate it to better match your training data. And this is traded off against not getting too far from your prior so that you can regularize. And normalizing flows can be used for what's called domain alignment, where you try to make learn the mappings that will make two distributions similar. And so I had this student that got a master's here. Now he's in Potsdam doing a PhD in a climate lab. Take the ideas from domain alignment and normalizing flows and show that this gives you a generative AI approach to doing data downscaling that is unsupervised. What I mean by unsupervised is, so here we're looking at precipitation maps, and these are actually from NWP and reanalysis at the two different scales. You don't need to know that the coarse scale, that you don't need to know what is the fine scale map corresponding to any particular coarse scale map. You literally just need access to fine scale maps and coarse scale maps for the same variable. And then you can train normalizing flows such that you've got a mapping from one domain, say coarse scale, to your latent representation, the posterior of your latent space, and similarly from the fine scale to that same latent space. And via this shared latent space, now you can sample as much as you want unconditionally, or conditioned on any particular precipitation map at either coarse or fine scale. You can sample conditioned on that and get something at the other scale. Or you can do these interpretability studies like this temporal interpolation. So what's visualized here, after the model had been trained, we are just given the two endpoint figures on the top row, which are fine scaled precipitation maps at two different times from one form of data. I believe this was actually the WRF. We actually used finer grained NWP, and we're upscaling to the domain of ERA interim product at the time. But then, since the model is can be run both ways, you could also downscale. But what you can do is you can map each of these to a point in latent space. From that point, you can generate the coarse grid map or sample as many of those conditioned on this fine-scaled map as you want, but you can also connect the dots. You can take a walk through latent space, and at each point in latent space, then you can generate coarse and fine-grained images. There's a whole literature in ML on how do you take this walk, because you're trying to actually walk a geodesic on a posterior that now no longer needs to be Gaussian. There's some efficiency issues. It's sort of an optimization problem. But this is how we can get a handle on how would this AI interpolate in time at coarse scale or fine scale such a precipitation map. So let's see, I do want to, end on time and leave time for questions. That first vignette talked about addressing spatiotemporal non-stationarity, which, as I mentioned, was open at the time, even in theoretical machine learning for online learning. And that idea of prediction at multiple time scales simultaneously was also not something I had seen. The avalanche example is not really a new algorithm, but an interesting twist or an unorthodox way of doing things when you have very limited supervision for anomaly detection that does turn out to perform well. And then leaving this checkbox as, largely open, this is meant to stand in for all the areas of machine learning, or mostly, let's say, the field of computer vision that claim to have solved a problem, but solve it with respect to the assumptions of pictures of cats on the web, right? So spatiotemporal, like AI for spatiotemporal data, if you go to your top computer vision conference, you'll find many papers with that title. But they're using video, and video has some nice properties, right? It has a foreground, a background, it has certain notions of depth. Now I'm just saying, oh, let me look at this real valued field over time. So yeah, I can treat it as video, but a lot of those assumptions aren't going to hold. So anyway, or the idea of a deformable pattern. I mean, is it a person or a cat? That's deformable according to computer vision. Whereas if you're looking for patterns emerging from fluids, forming a storm and then dissipating, that's quite deformable and ephemeral, and is not treated in the standard works. So this means that there's scope for algorithm design, if that's what you're interested in. So yeah, I would say that the data in this domain is pretty unique and is a strength, but the limitation is in the temporal dimension, right? The measurements only came online relatively recently compared to geologic time and the timescales that we care about for reasoning about climate change. And there's no counterfactual Earth. We can't see what would have happened if, other than in climate model simulations. But we are starting to have data products that are highly geospatially explicit. So one idea in order to train algorithms that are data hungry is to kind of substitute the diversity that we have and large amounts of data that we have over space for what we lack in time. Maybe we can study regions where different climate interventions had been taken and compare those different regions, since we don't have different histories of our whole planet. I mentioned a little bit about scale resolution in terms of this general generative AI approach for downscaling. But there's other folks you should talk to who are actually trying to address some of those scale resolutions inside a climate model. And this is the field of parameterization, and there's emerging AI work in that domain. Definitely, we're interested in getting rid of these IID assumptions. We've talked a little bit about some lightweight online learning algorithms. To do that, we want to do probabilistic forecasts. We want to be able to evaluate them, but often even our evaluation metrics do depend, like root mean squared error depends on IID data, even CRPS to evaluate quantile forecasts. Well, that's comparing it to a cumulative distribution function. What does that mean? That there's some stationary distribution. And then this also gets into ideas of interpretability. So generative models generate basically a probability distribution over outputs. how do we understand or quantify this? Well, this is important when generative AI is used for clouds or precipitation. You need to understand it. And this is actually still open in core ML for the most part. Oh, and then just kind of signposts that are really motivating me, those pictures of extreme weather. We needed solutions yesterday. And then also climate justice, because introducing any kind of technology, including AI-driven decision support or forecasting tools, instead of just doing no harm, we should be trying to act to undo the legacy of climate injustice. And much of the work I discussed is from my Boulder lab, also building up a Paris lab, and submit to the journal. I don't know if there's any press folks at your event, but they're around and they're really wonderful and helpful and great to work with. And then also kind of a partner that you guys might not be aware of. Recently, the National Science Foundation funded what's known as a data synthesis center, headed out of my university, but collaborative with other places, including the University of Oslo. And it's really forming a platform for accessibility and inclusion in the realm of data science for environmental problems. It's not specifically related to climate, although that's definitely an area, and it'll fund working groups to take retreats in Boulder. It had a big summit, which was an unconference style event where there were emergent topics, and I would just encourage you to keep your ear out for opportunities there. Where the next thing to be announced will be a hackathon. So I'll stick around for some questions.
Thank you so much, Claire. Yeah, we have time for some questions, and if you just wait for a mic to ask your question so that the people online and the recordings can catch it, that would be super.
Hi, Claire. Everyone's shy, so I'll break the ice and I'll ask a question first. It's Dominic here. So thank you for that lovely talk. I was interested in the avalanche part about the sort of cascading problems. So I wondered to what extent you could use these techniques for doing sort of risk modeling, where you could say, well, here's the probability of one of these kind of rare but catastrophic events happening in this area, kind of run it almost backwards rather than kind of forwards, like predictive style, like, okay, here's the probability or possibility of this happening within this time frame. Is there a way of kind of adapting?
That's a great point. That's a great point. And anytime, so we haven't done that, but I think that's cool. And the idea is that we're using this pipeline now to just detect past avalanche, okay? But there's no reason that you couldn't take this model and run it generatively, okay? So then you can kind of simulate a lot of different conditions, and then you could, compare them to this threshold. Or alternatively, instead of having a threshold here, we could, instead of doing classification, we could output a probability. Or maybe we could be looking for multiple kinds of extremes and have multiple thresholds, or some other kind of logic for how we make our final prediction. So that's interesting. The student who did this as one of her earlier thesis chapters and now is graduating was saying that the field of unsupervised and semi-supervised learning, where you design your own pretext tasks, has gone by so quickly just in the couple of years since she wrote this paper, that she would really love to also go try out other generative models there. And so then you could get more informative distribution. So for example, using a normalizing flow, we don't just need to have a Gaussian over sort of images. So that would be an interesting idea. Now, it's going to be hard to generate avalanche from this because the majority of the image patches don't have it. But you could imagine using this to just generate a lot more data, which would then help you in some other downstream task. Maybe I want to use the method of analogs, is what I'm seeing now, you know, similar to something that did have an avalanche in it, for example. So yeah, I think there's a lot of scope in what you said. I'm just off the cuff brainstorming, but that's great.
Yeah, great. Thank you. Yeah.
Next question. Could you just say where you're from as well, please?
Yeah, Claire, this is Ivo, University of Reading. I was wondering, to what extent does the methods that you presented in the first two signets, especially the first one, the non-spatial part, differ from data assimilation?
I like that question. The first time, so I was not calling it data assimilation, but somebody who saw my talk said, oh, this is data assimilation because you're looking at observations. And so I would say that this addresses the problem of data assimilation without using any of the methods that we typically call data assimilation, like no Kalman filters or ensemble Kalman filters were harmed in the design of this algorithm. But yes, the general framework that we're going to use models and observations to train AI could be termed as post-processing or data assimilation. And from an AI perspective, it's an important paradigm to treat the output of physical models as input data, because otherwise we wouldn't have enough data, especially when we want to think about things like rare events and extremes or tipping points or things that are going to change. But yes, and there's actually, so Anastas Charantonis, who's in the Paris region and is joining my team at INRIA, he kind of sees it, and also Julien Brajar is another one to look at, who's now in Norway, but is usually at Sorbonne. He kind of sees it as, you know, viewing like what ML can do for climate and weather in the lens of data assimilation. How can we kind of like exploit the relations between them? So yes, certainly this project would count as such.
Thank you.
But just a different way than what you're going to see probably in some of the other literatures for that.
Super. I think we have time for one more question. Anyone else?
Hi there, Chris Kent from the Met Office here. You showed a lot of different examples there. If you take like the hurricane forecasts, are they being used by forecasters now as an extra tool? And if not, what do we need to do to convince people to start using them?
Yeah, so I have not followed things all the way rubber to the road with this work. I know Amy McGovern, for example, has made sure that AI is embedded in some of the tornado and hail forecasting systems that are used in the US. Basically, we talk to and collaborate, we sort of the people working on climate informatics, with people at NOAA, certainly Met Office, you know, DeepMind and Google have worked on precipitation nowcasting, and now they're trying to do foundation models that are general and can be used for downstream tasks of different weather forecasting techniques. And Google, you know, talks to a variety of governments. The IMD is using some of the AI-based tools in India to forecast at, you know, several month lead times precipitation extremes that'll result from the next summer monsoon of various types. And I know that because Mumita Saha sort of had been working with IMD before she came and did a postdoc with me and then ended up back in India. So definitely when I visited once, both the Korea Meteorological Department and folks in Japan do use AI. So what you're sort of, I guess what I'm saying is the research is seeping in, To what extent things are being used in an operational product, I'm not 100% sure.
Thank you.
Okay, I think we should thank Claire once more for her fantastic talk. Thank you so much.
Have a great summer school. Bye-bye.